So let's talk a bit more about expressions here, and especially in the context of pops. We will learn stuff that we can use in any context, of course, but especially for pops this makes sense. And the first thing when it comes to expressions is that we can use them to move stuff. So for example, we've learned with in the first expressions video that we can use $f or ff, which you should make a habit of using. But you could also use t, for example, to animate anything over time in a linear fashion. So this is a bit fast because my real-time button isn't on. So here you can see something grows constantly over time. This is something we can already do. But what's often very helpful, especially in simulations, if we want to have some kind of natural back and forth movement. And for this, of course, we can use the sinus function. So for example, if you wanted to have kind of a buoy or something, we can use the sine function that is filled with some kind of float. And what makes sense usually here is $ff. Oops, not 3, but 2. And what you can see here is now that our sphere moves up first, but then moves down again. As you can see, it's a bit slow, but what we can do is we can just multiply the input, for example, with 15 to speed it up 15 times, and then you can see it moves up and down. And also, as every sine function, it comes out, the numbers come out between -1 and 1. So let's multiply that with 2 to increase the amplitude so that our sphere will move up and down between -2 and +2. So this is pretty cool. Another thing you can do with sine and cosine especially is that we can combine the two to create a circular movement. So if you need something that just moves around in circles, you can, sure, there are many ways of animating this, but sometimes it's really handy to know that you can just fill the x component with a sine function. So let's do the ff multiplied by 10 again. And then this will just move it in x back and forth. But if you combine this with z, which is this direction, you can just add the cosine function to this, maybe with the same numbers, $ff multiplied by 10, like this. And if I run this, you can see we actually created a circular movement. Now, to make the circle bigger, of course, we have to multiply both and increase the amplitude, because currently the radius is exactly 1. Not the radius, actually the diameter is exactly 1. And by multiplying both with 3, for example, we can make our circle bigger. And now, actually I take it back, it was the radius. So with a radius of 3. There you go. So we can control speed, we can control the radius. And as you can imagine, when we use different parts of that, different multipliers for it, for the two parts, then you can see that it becomes, you know, a more oval shape. Also, what can be kind of funny is when you give it different kinds of speed inputs, because then you get some kind of really weird movement. In this case, it's kind of an 8. So it's, you know, it's not absolutely necessary, but if you play around with this a little bit and get used to it, you just have another tool in your arsenal that you can use to relatively quickly create mathematical animations. Now, another cool thing you can do with expressions is actually you can create randomness in noise. So let's start with noise, and there's actually a noise expression. So for example, if we have this buoy here and we're too lazy to animate this by hand, we can, if we wanted to put it into a storm or something, fake that by changing the rotation with a noise expression. So let's type in noise and let's see what the rules here are. It needs actually, for some reason, 3 inputs. And unfortunately down here, this tx, ty, tz is a bit confusing. What you need here is just the time, and you can use different numbers, but you can also put the same number in. So what we will usually do is we start with $t for the current time in seconds. If you try frames, it will be too fast. So let's jump into using t right away so that you can see the result. And if I run this, you can see there is a slight movement, just like we saw a little bit with the sine waves. So let's increase the strength, because of course what comes out of a noise function is a value between 0 and 1. So let's multiply that, for example, with 10, and then we should see it better. And now here you can see It's a bit like a sine function, but it's much more, random, because it's a noise, which gives a very natural kind of feel to it. Now let's do the same for the other parameters, for y and z as well, and then you would get this. And the problem with that is they all now get the same noise values if we just copy it. So usually what you do is you change them a little bit. If you would multiply or divide the time, here you would speed up or slow down the noise, which you can play around with. But if you just want a different result, usually subtracting and adding is a good idea, because then you will not change the speed, just the number. And I usually just change that for 2 of the parameters to something that is different to the rest. Can be anything you want, because it doesn't really matter. It's kind of random anyway. And now if we look at the result, we will get different results, and the buoy is kind of moving in a kind of realistic way. Let's make it a bit stronger by multiplying all 3 by 20, and you can see those expressions can get a little bit long. And then you have something like this. And I think it's kind of nice, because it kind of feels natural, as if there are some kind of forces that are pulling and pushing on this thing. And maybe what we can do to finish this up is doing the same on y, but here we will maybe lower it to only ½ a meter. And let's see how this looks like. Yeah, there you go. And this is a nice way of creating some kind of, artificial animation. Another thing you can do actually with the noise function is it's often used to create a shaky camera. For example, what we could do with a scene like this, a very simple destruction scene, and this is an example of something we will look at later on. To make this shot a bit more interesting, besides, making it look better, we could add a shake to the camera. So here's the camera, and it already has some numbers, so we can just add to the existing number a noise, and we fill again the t in it for the current time in seconds. And this is currently only the rotation around x, but let's see how this looks like. You can see there is movement in the camera now. So to speed this up, we can multiply the time, maybe by 2 to speed it up twice. And I want to do it for x first, yes, maybe something like that. And then multiply the result by 0.5 to make it less strong. And yeah, that's not too bad. And let's copy this now, only the noise, for the other rotations. So we add another noise for this one. And again, the best approach here is to maybe afterwards subtract or add a random number to get different results for this. And I do the same for Z. And I hope I'm not repeating the numbers. So something like that. And then you can see now the camera is shaking. Let's go back to the beginning while this is happening. It's not the best shake in the world, I get it, because I just typed in random numbers. If you play around with this a little bit more, you can get better results. But what we have right now is a shaking camera, of course, not a shaking geometry. And here you can see that's a nice way of creating a handheld camera. So a noise expression can be pretty helpful for stuff like that. Another function that can be helpful is the random function, or the random expression. And let's say we take our very ugly cartoon tree from the very beginning, and we wanted to create different heights of this version and save them out for every frame. What we can do then is just use a transform and put in for the uniform scale a rend function. And when we look into the help, you can see it just needs one value. And in our case, we just use the current frame. And that will mean we will get a different height for this, or a different scale for every frame that we run this. Now, it's not useful for animations or anything, but this can be helpful, just literally create randomness over a certain amount of time if you want to export this, for example. But you also can use that for animation if you want. I couldn't come up with a better example than a salt shaker, because that would be something that moves in a very erratic way. So here this is currently not moving, and all we have is a particle simulation where the front is emitting points and then they fall down, nothing too special. And we want to make this shake, and instead of using a hand animation, we could use a transform before this shaker is actually rotated in space, so it stands on the ground first, and we want to, radically move that thing up and down. Sure, you could use a noise for this, which is probably a better choice, but a rend would work just as well. So for the translate Y, I use a rend and the current frame, and that will move that thing up and down pretty quickly as long as I look through the transform, and then it looks like this. Yeah, and let's say that's a bit too strong, even though actually, no, I think that's pretty good. Let's leave it at that. And when we look at the result, when we run this through the simulation, we get this result, which, yes, is a bit stupid. I had to come up with some kind of idea what to do with that. So that's the noise and rent expression, pretty helpful for all kinds of stuff. So maybe it can help you in your setups as well. So another thing is when it comes to expressions, and let's go back to a normal sphere here, because we want to use this as a normal source for our pop network. We can just scatter points, and we can actually control our birth activation parameters, which actually exist exactly for that reason. So if you ever wondered why we have a goddamn float controller here, not just the checkbox or something, the very reason is that you can fill this parameter now with expressions. And what you will see quite often is that people, when they want to just kind of create a start case with a finite number of points, we could do the following. We could either delete the pop source to scatter the points ourselves, and then take those points as an initial state. So we don't source constantly new points, but we use this initial geometry and read in the first input with our horrible OP input path. There you go. And now what you will see, let's add a gravity to this to show this. Oh, actually, let's make it pop force, it's more interesting. You can see that it's a finite amount of points. They're not new points added to it. So not a surprise, that's what the initial geometry is for. But sometimes you will see people do this. They don't use the initial geometry, but they actually do use the pop source, because they put in an interesting little trick. They control, first of all, maybe not a constant birth. Well, actually it doesn't matter, but in this case it makes more sense with the impulse count, because this way I can define exactly how many points I want in the beginning. And they control this with an expression saying, for example, only emit points on the very first frame. And you could do this by typing in $f equals, I don't know, in this case, my first frame. So this means, check the comparisons video if you're not clear about this. It means if the current frame equals 1, and actually, to be honest, I should have used $ff, then the result of this will be 1. If I change the frame to one more frame, then this is not true anymore, so it gives me back a 0. And this is a nice little way of making sure that, and I have to make sure that I actually take the first context, that I only emit points on the first frame, which in the end is kind of the same as using the initial geometry, with the difference that the pop source will scatter the points for me. I don't have to do it outside. This is kind of cool, but what if I change my frame range? You can make it even more elegant. You can just say, okay, if the current frame equals the current start frame of my scene. So this shouldn't be new to you, because we already learned f-start, ff, and the equal comparison operator. But this is kind of nice to see how elegant this is. It will always on the start frame create those 1000 points. Now what this also allows us, and this is different to the initial geometry, it actually allows us to let stuff happen only at a certain time. For example, let's emit those points only on the 10th frame, which just means for the first 10 frames, I chose this not wisely, maybe let's wait 30 frames. For the first 30 frames nothing happens, and then all of a sudden points are emitted, which is pretty nice, because we can now type in any number we want. We could even go further. We could say, okay, if the current frame is smaller than 30, then emit please, or in this time I actually use 10. And that means for 10 frames stuff will be emitted and then it stops. Pretty elegant. Now you could even say, okay, only after the first 10 frames should the emission begin, and then not even forever, but we can combine this. Remember from the first expression video, we can combine this with an end. And that means we can actually check for two things. And that is the current frame bigger than 10? And is it also smaller than, let's say, 30? And that means only between 10 and 30, this will be true. So this allows for even more complex rules, because now the points will be emitted after frame 10 and only before frame 30, which we didn't see well, but maybe lower it to 20, maybe we can see it then. But it then stops emission after 10 frames. So as you can see, pretty handy, and you can use this for any kind of parameter, of course. But in the context of pops, this is really quite handy. And maybe let's combine the two things and then finish this video by using our circular movement trick here. There you go. Now it's actually circular again. There you go. And in combination with our time expression, we should see that the first, actually, let's shorten this to maybe here. Oh yeah, I changed it to 50 for some reason, don't know why. So let's rewind. So now after only 10 frames, and then it stops again after 20, because the 30 frames are reached, only then will he emit. So it's kind of cool that you can do this, and all this with expressions as another tool in your pop arsenal. So I hope this is helpful. Thanks very much and see you later. Cheers.